Far out in the frozen depths of our solar system, hidden beneath a thick, golden haze, lies a world that should not exist. A world with rivers carving through valleys, with great lakes sprawled across its surface, and with waves crashing on alien shores. But this is not Earth. This is Titan, Saturn's largest moon, and the liquid that fills its seas is not water, but liquid methane, flowing at temperatures colder than any winter night we have ever known. It's a landscape so eerily familiar, yet so profoundly alien, that it challenges everything we think we know about where life can take hold. And today, we are going on a journey to its most profound secret, a vast global ocean of liquid water, hidden deep beneath the icy crust, where chemistry we are only beginning to imagine could be unfolding right now. This isn't just a story about a distant moon. It's a story about possibility. For decades, we've scanned the stars, wondering if we are alone, searching for planets bathed in the warm, life-giving light of their suns. But Titan presents a radical, almost heretical idea. What if the recipe for life doesn't require a sun at all? What if the building blocks can be forged in absolute darkness under immense pressure, using a completely different set of ingredients? The chemistry happening within Titan's subsurface ocean could be a parallel path, a shadow biosphere operating on principles we are only starting to decipher. It forces us to expand our definition of habitable and confront the thrilling notion that the universe might be teeming with life in forms we have never dared to dream of. So let's pull back the veil on this enigmatic world. We will descend through its complex atmosphere, navigate its hydrocarbon seas, and drill down through ice as hard as rock to explore the hidden ocean below. We'll uncover the bizarre chemical reactions that could be taking place, reactions that might not just mimic the early Earth, but invent entirely new rules for biology. This is more than astronomy. It's a detective story, a search for clues to one of humanity's biggest questions. And by the end of our journey, you will see our solar system and the potential for life within it in a completely new light. To truly grasp the strangeness of this world, we first need to understand its scale and its place in our cosmic neighborhood. Titan is not a small, insignificant moon. In fact, it is a giant, larger than the planet Mercury and second in size only to Jupiter's Ganymede among the moons in our solar system. But its true distinction, what sets it apart from every other known rock and ball of ice, is its atmosphere. While moons like ours are barren and airless, Titan is wrapped in a dense, smoggy shroud of mostly nitrogen, a eerie parallel to our own air, but one that is 4 times thicker at the surface. This thick blanket creates a surface pressure similar to what you'd feel standing at the bottom of a swimming pool here on Earth. It's this atmosphere that, for centuries, hid Titan's greatest secrets from our telescopes, presenting only a featureless golden-orange sphere, a mysterious orb hanging in the darkness around Saturn. That all changed with the arrival of a robotic explorer from Earth, the Cassini-Huygens mission. The Cassini spacecraft, which orbited Saturn for 13 years, used radar and infrared cameras to pierce that perpetual haze. What it saw was nothing short of revolutionary. The Huygens probe, which detached from Cassini and parachuted through the atmosphere in 2005, sent back the first breathtaking images from the surface. They revealed a landscape that was hauntingly familiar yet utterly alien. We saw rounded pebbles of water ice smoothed by flowing liquid in river channels that drained into vast, dark basins. We confirmed the existence of great polar seas and countless lakes, some rivaling the size of North America's Great Lakes, but the liquid wasn't water. On the frigid surface of Titan, where temperatures average around -290 degrees Fahrenheit, water is frozen solid, as hard as granite. The liquid that carves these channels and fills these seas is hydrocarbon, a mix of liquid methane and ethane, the main components of the natural gas we use on Earth. So picture this world, a landscape where the bedrock is solid water ice, darkened by complex, tarry organic compounds that rain from the sky, where the cycle of erosion is driven not by water, but by liquid methane evaporating from seas, forming clouds and falling back as rain. Where the shorelines are not sandy, but perhaps slushy with a strange, sticky material. This is the stage that Cassini-Huygens revealed, a world with an active geology and meteorology that mirrors Earth's in its processes, but uses a completely different and deeply chilling set of ingredients. It's this bizarre combination of the familiar and the foreign that makes Titan such a compelling target in our search for life, because it proves that the processes that shape planets can work with all sorts of chemistry, under conditions we once thought were impossible for anything dynamic to occur. And it is upon this alien stage that we find its most spectacular features, the great polar seas. If you were to fly over Titan's North Pole, you would witness a sight that, from orbit, looks almost like a fragment of Earth itself. Vast, dark expanses of liquid span the landscape, the largest of which is known as the Kraken Mare. This is not merely a lake, it is a true sea, covering an area larger than the Caspian Sea on Earth, a sprawling body of liquid hydrocarbons so immense that it has its own coastline, with bays, straits, and likely even complex currents flowing beneath its surface. Nearby lies Ligeia Mare, another colossal body, so remarkably smooth and radar dark that it appears almost like a sheet of black glass, reflecting the hazy sky above. The very existence of these liquid bodies is a testament to the extreme cold that defines this world. Here, at nearly 300 degrees below 0 Fahrenheit, the chemistry of what can be a liquid is completely inverted from our earthly experience. For us, water is the universal solvent, the fluid of life. But on Titan, water is part of the landscape, frozen into a substance as unyielding as bedrock. The role of water is instead played by methane and ethane. These simple molecules, which are gases here on Earth, are chilled into a liquid state on Titan, creating a solvent that can flow, evaporate, and condense. This establishes a full, active hydrological cycle, but one made of hydrocarbons. Methane evaporates from the seas, rises into the thick atmosphere, and forms clouds. These clouds then release a slow, gentle rain of liquid methane, which trickles and flows across the icy terrain, carving river valleys and canyons that look strikingly similar to those formed by water on Earth, before finally draining back into the seas. Imagine standing on the shore of the Kraken Mare. The ground beneath your feet would be a mixture of water ice and dark, organic gunk, a substance that has settled out of the atmosphere over eons. The water before you would not be clear and blue, but likely a murky, dark brownish-orange, thick with dissolved hydrocarbons and other complex organic compounds that have washed in from the land. The waves would not be made of water, but of liquid methane, crashing with a different viscosity, a different weight, against an icy shore. And the rain falling from the orange sky would be a liquid that, to our senses, would feel bitterly cold, yet it is this very rain that sculpts the entire landscape. This cycle of methane, from sea to sky to river and back again, is a powerful echo of our own planet's water cycle, proving that the fundamental processes that shape a world are not unique to Earth. They can operate with whatever chemicals are available under conditions we once considered utterly hostile to any form of dynamic activity. But this astonishing landscape of methane rivers and hydrocarbon seas is only the surface layer of Titan's story. To uncover its deepest mysteries, we must look beneath our feet, through the very ground we stand on. That bedrock of water ice is not a solid, permanent foundation stretching all the way to the moon's center. Instead, it is more like the crust of a gigantic cosmic egg, a shell that may be dozens of miles thick, and it hides a secret of profound importance. For decades, planetary scientists pieced together clues from the Cassini mission that pointed to something incredible. This entire icy crust might be floating. It is not firmly anchored to a rocky core below, but is instead decoupled, separated by a global layer of liquid. Titan, in its entirety, appears to be a world with a subterranean ocean. The evidence for this hidden sea came from watching Titan itself wobble. Just as a raw egg spins differently from a hard-boiled one, a moon with a liquid layer inside will behave differently as it orbits its planet. Cassini's precise tracking of Titan's gravitational field and its rotational motion revealed a slight but telling libration, a wobble in its spin. This was the crucial clue. A solid moon, frozen through and through, would have a much more stable rotation. The detected wobble strongly suggested that the icy shell we see is mechanically independent from the dense, rocky core deep below. They are not locked together. The shell is free to shift and rotate slightly over the liquid layer that separates them, like a slippery peel sliding around the fruit inside. This revelation transforms our understanding of Titan's internal structure. Imagine a layered cosmic onion. At the very center lies a silicate rock core, heated by the lingering decay of radioactive elements, much like Earth's own interior. Enveloping this warm core is that global subsurface ocean, a vast body of liquid water that could be dozens of miles deep, and encasing everything is the thick outer shell of water ice that forms the moon's surface. This architecture creates an environment of staggering possibilities. The ocean is kept liquid by a combination of factors: heat from the core below and the insulating effect of the icy crust above, which traps that heat like a thermos. Furthermore, the ocean is likely not pure water. Models suggest it is a briny soup saturated with ammonia and various salts, which act as a potent antifreeze, depressing the freezing point and ensuring the ocean remains liquid in the deep cold of space. This setup creates what scientists call a water world sandwiched between two fundamentally different environments. Above the ice shell, we have the bizarre, cold hydrocarbon chemistry of the surface. Below it, in the dark, high-pressure depths of the ocean, we have an aqueous environment that, in some respects, feels far more familiar. It is a place where water is the solvent, where chemical reactions we understand from Earth can potentially occur. But it is also an environment of extremes, utterly cut off from the energy of the sun, existing in perpetual darkness under the immense weight of the ice above. This isolation is what makes it so fascinating. Any chemistry or even biology that might exist in that deep ocean would have to be entirely independent of solar energy, relying instead on chemical energy sources, perhaps from hydrothermal vents on the ocean floor where the warm core interfaces with the water. The icy shell is not just a barrier, it is a protective lid sealing in this hidden world and allowing it to follow its own evolutionary path, separate from the complex organic processes happening on the surface. It creates two potential kitchens for life on a single world, each operating with a completely different set of ingredients and rules. Now, how do we know for certain that this hidden ocean exists when it's completely invisible to our cameras and buried under an ice shell that might be 60 miles thick? The proof comes not from a single photograph, but from a brilliant piece of cosmic detective work, where scientists measured Titan's subtle movements and its very shape to deduce what must lie beneath. One of the most compelling lines of evidence is Titan's wobble. As it orbits Saturn every 16 days, it doesn't spin with the perfect, rigid stability of a solid ball. Instead, it exhibits a slight rocking motion, a libration, as if its outer shell is loose. Think of it like this: if you spin a hard-boiled egg, it rotates smoothly. But if you spin a raw egg, the liquid sloshing inside causes the shell to wobble in a distinct way. Cassini's precise measurements revealed that Titan behaves like that raw egg. The icy crust we see is not locked firmly to the interior. It can shift and rock independently, which strongly implies a liquid layer is lubricating the interface between the shell and the core. This picture was further confirmed by examining Titan's shape itself. A world that is entirely solid and rigid would be shaped almost perfectly by its own gravity, forming a sphere. But Titan is slightly squashed or oblate, bulging at its equator more than a completely solid body should. This flexible, squishy response to the gravitational pull of Saturn suggests that Titan's interior is not uniformly solid. Some parts must be deformable, and a global liquid ocean is the most elegant explanation for this global flexibility. It's as if the entire moon is yielding to external forces in a way that only a layered, partially liquid structure can. Adding the final piece to the puzzle, Cassini's analysis of Titan's gravity field provided the depth of that ocean. By tracking how the spacecraft was ever so slightly tugged by Titan's gravitational pull during its many flybys, scientists could map the distribution of mass inside the moon. The data fit a model where a dense, rocky core is surrounded by a much less dense layer, that global ocean, which is in turn capped by the low-density ice shell. Putting all this evidence together allows us to sketch a remarkably detailed profile of this alien abyss. The hidden ocean of Titan is not a small lake tucked under the ice. It is a vast global sea, likely enveloping the entire moon. Current estimates suggest its depth is staggering, perhaps reaching between 50 and 100 miles. To put that in perspective, the average depth of Earth's oceans is only about 2.5 miles. Titan's ocean could be 20 to 40 times deeper, containing a volume of liquid water many times greater than all of Earth's oceans combined. And crucially, this immense body of water is thought to be in direct contact with the moon's rocky, silicate core. This point of contact is where things get truly interesting for the possibility of life. On Earth, we find entire ecosystems thriving in the absolute darkness of the deep ocean, clustered around hydrothermal vents. These vents spew mineral-rich, superheated water, providing both the energy and the chemical building blocks for life without any need for sunlight. On Titan, the heat from the radioactive decay within its warm, rocky core could be driving similar hydrothermal systems at the ocean floor, creating potential oases of chemical energy in the perpetual night. This sets the stage for chemistry that could, in theory, follow a path startlingly similar to the one that may have sparked life on our own planet. But with this picture of a hidden aquatic world, we confront one of the most profound questions in all of science: is water the only possible cradle for life? For centuries, our perspective has been unavoidably shaped by our own existence. We are, after all, beings of water. Every known life form on Earth, from the tallest tree to the deepest sea microbe, relies on water as its essential solvent, the liquid medium in which the complex dance of biochemistry unfolds. It dissolves nutrients, transports molecules, and facilitates the reactions that define living systems. This has led to a deeply ingrained assumption in our search for life elsewhere: follow the water. But Titan, in its magnificent strangeness, presents a powerful and compelling argument that this view might be a case of what's called carbon chauvinism or water chauvinism. We are, in essence, looking for life that looks like us, based on the only blueprint we have. Titan challenges us to consider that the universe might have written other blueprints, using a completely different set of chemical ingredients. The key to any form of life, as we understand it, isn't necessarily the water molecule itself, but the functions it performs. A good solvent for life needs to do a few critical things. It must be a liquid over a wide range of temperatures to allow for stable, ongoing reactions. It needs to be able to dissolve a wide variety of different molecules so they can mingle and interact, and it should be relatively stable, not breaking down too easily. Water is brilliant at this, which is why it works so well on Earth. But what if another liquid could perform these same essential functions under different conditions? This is where Titan's surface chemistry becomes a laboratory for alternative possibilities. The liquid methane and ethane that fill its seas and rivers can also act as solvents. In their chilly realm, they are stable liquids, and they are excellent at dissolving non-polar organic compounds, the very kinds of complex carbon-based molecules that the Cassini mission found in abundance in Titan's atmosphere and on its surface. Imagine a different kind of biochemistry, not based in water but in liquid hydrocarbons. The reactions would be slower due to the intense cold, and they would follow different chemical pathways, but the potential for complexity is undeniably there. This idea gives us two parallel yet isolated potential kitchens for life on a single world. Deep below the ice in the subsurface ocean, we have the familiar potential of water-based life. Here, the chemistry could be similar to what we find around Earth's hydrothermal vents, where organisms chemosynthesize, using chemical energy from the rocky core instead of energy from the sun. It's a dark, high-pressure biology, but one that operates on principles we can recognize. Meanwhile, on the surface, a truly alien biochemistry could potentially be unfolding in the methane lakes. Instead of cells with water-based cytoplasm, you might have cells with membranes made from different molecules, perhaps nitrogen-based compounds like acrylonitrile, which could form stable, flexible structures in liquid methane. The energy for such life wouldn't come from the sun or from hydrothermal vents, but could be drawn from chemical reactions in the atmosphere itself, like the conversion of acetylene and hydrogen, which Cassini detected evidence of on the surface. It's a speculative idea, but it forces us to expand our imagination. Life on Titan's surface wouldn't just be extremophile life, toughing it out in a harsh place. It would be alien life built from the ground up on a different foundational chemistry. So, the existence of Titan's dual environments, the surface hydrocarbon seas and the subsurface water ocean, doesn't just present two chances for life. It presents the possibility of two completely independent origins of life, following two different sets of rules on the same world. One would be a shadow biosphere, a parallel existence operating in a medium we consider hostile. This radically broadens the concept of a habitable zone. We no longer need to look only at planets orbiting at just the right distance from their star for liquid water to exist. We can now consider icy moons in the outer solar system, warmed not by sunlight but by the internal heat of gravitational squeezing and radioactive decay, as potential havens for biology. Titan stands as a testament to the universe's boundless creativity, suggesting that the ingredients for life might be far more common, and the forms it might take far more diverse than we ever thought possible. This brings us to a pivotal question. If life were to emerge in Titan's methane seas, what would it be built from? On Earth, life is encapsulated. Every living cell is surrounded by a membrane, a flexible barrier made primarily of molecules called phospholipids. These form what's known as a lipid bilayer, a structure that is stable in water, creating a tiny, self-contained vessel for the chemistry of life. But on Titan, in seas of liquid methane that are hundreds of degrees colder, a phospholipid membrane would be useless. It would instantly freeze, becoming brittle and inflexible, or simply dissolve. For life to exist in such an alien solvent, it would need an entirely different kind of architectural blueprint, a membrane built from molecules that are stable and functional in a cold hydrocarbon soup. This is where Titan's atmosphere becomes a cosmic chemistry set of breathtaking complexity. High above the surface, in the upper haze layers, sunlight and energetic particles from Saturn's magnetic field bombard the abundant nitrogen and methane. This constant input of energy triggers a cascade of chemical reactions, linking simple atoms into increasingly large and complex organic molecules. It's a process that creates a steady rain of complex hydrocarbons and nitriles, carbon-nitrogen compounds that slowly drift down to coat the surface. For years, scientists studying data from the Cassini spacecraft identified a whole zoo of these molecules, but one particular compound detected in Titan's atmosphere stood out as a potential game-changer, a molecule called acrylonitrile, also known as vinyl cyanide. On Earth, acrylonitrile is an industrial chemical used to make plastics like acrylic fibers, but on Titan, it could be the key to biology. Laboratory experiments have demonstrated something remarkable. When acrylonitrile molecules are present in liquid methane at Titan-like temperatures, they don't just float around randomly, they can spontaneously self-assemble into microscopic hollow spheres. These structures, which researchers call azotosomes, are astonishingly similar in function to the lipid membranes of cells on Earth. The word azotosome itself tells the story. Azote is an old name for nitrogen, and soma means body. They are quite literally nitrogen bodies. These tiny spheres are flexible, stable, and can act as a boundary, potentially allowing for the concentration of different chemicals inside a protected compartment. This is not life itself, but it is perhaps the most fundamental prerequisite for it, a way to create order out of chaos, to separate the inside from the outside, to make a home for biochemistry to begin its work. Imagine these azotosomes floating in the dark, slow-moving currents of the Kraken Mare. They would be invisible to the naked eye, microscopic bubbles drifting in a sea of liquid methane. Their stability comes from the unique properties of the acrylonitrile molecule, which has a structure that allows it to arrange itself in a sheet that curves into a sphere, all while remaining dissolved and flexible in the frigid hydrocarbon liquid. This is a scaffolding for life that is completely independent of water. It suggests that the basic step of forming a cellular structure, a step we once thought was uniquely tied to water-based chemistry, might be a more universal process, achievable with the right ingredients under the right conditions. And on Titan, those ingredients are being manufactured in vast quantities in the sky above and are readily available on the surface. The discovery of acrylonitrile and the potential for azotosomes transforms Titan from a merely interesting world into a prime candidate for a truly alien biochemistry. It provides a plausible answer to the container problem for life in a non-water solvent, but a membrane is just a starting point. The next, even greater challenge is what would happen inside that membrane. What would serve as the genetic material? What would power the metabolic reactions? The chemistry would have to be fundamentally different, operating at a much slower pace due to the intense cold, and likely relying on different elements and reaction pathways than those used by terrestrial life. Yet, the mere existence of a potential building block for cellular structures opens a door to possibilities we are only beginning to explore. It tells us that the principles of life compartmentalization, energy utilization, and information storage might be achievable through multiple chemical avenues. Titan's surface, with its complex organic haze and vast methane seas, offers a naturally occurring laboratory where these alternative rules for existence could be written. But if azotosomes provide the potential containers for life, what would fill them? Where would the raw materials come from to build something truly complex? The answer lies in the very substance that gives Titan its distinctive rusty orange color, a complex organic goo known as tholins. This isn't just dust or simple smog. It's the product of a planet-wide chemistry experiment happening in the sky, a process that transforms simple gases into the complex building blocks of life as we know it, and perhaps of life as we don't. The creation of tholins begins high in Titan's upper atmosphere, where the moon is bathed in a harsh bath of ultraviolet light from the distant sun and bombarded by energetic particles trapped in Saturn's powerful magnetic field. This constant energy barrage is like a cosmic lightning strike, but one that happens continuously. It smashes into the simple, abundant molecules that make up Titan's air, methane, and nitrogen. These impacts break the molecules apart, creating a soup of highly reactive fragments, carbon radicals, nitrogen atoms, and charged ions. These fragments are desperate to bond with something, anything, to become stable again. In the low-pressure haze of the upper atmosphere, they collide and stick together, forming ever larger and more complex chains and ring structures. They polymerize, linking up into large macromolecular clusters that are far more intricate than the gases they came from. This process, effectively, is a form of artificial synthesis, mimicking the kinds of chemical reactions that might have occurred on the early Earth before life began. The result is a substance that scientists have named tholins, from the Greek word for muddy or unclear, and the name fits perfectly. Tholins are not a single, well-defined compound, but a vast family of complex organic polymers, a tarry, reddish-brown gunk that is incredibly rich in carbon, hydrogen, and nitrogen. In laboratory experiments that simulate Titan's atmospheric conditions, researchers have created tholins, and what they get is a substance that looks like a sticky, dark residue. It's a material that is notoriously difficult to analyze because it's such a complex mixture, but we know it contains many of the molecular precursors essential for life as we understand it. Amino acids, the building blocks of proteins, have been found in simulated tholins. So have the nucleotide bases that form the rungs of the DNA ladder. It is, in essence, a prebiotic soup, but one that is manufactured in the sky and then distributed across the entire globe. This is where Titan's atmosphere becomes a delivery system. These tholin particles are heavy. They slowly drift down from the high haze, taking months or even years to settle, creating that perpetual golden-orange shroud that hides the moon's surface. They accumulate in the atmosphere, eventually falling out as a gentle, continuous rain of organic snow. This slow-motion snowfall coats the entire landscape, collecting in dunes made of organic sand and washing into the rivers and seas. Imagine the surface of Titan covered in a layer of this primordial goo, a sticky, complex organic material that has been accumulating for billions of years. The dunes near the equator are likely vast fields of this hydrocarbon sand, and the shorelines of the methane seas may be sludgy with it. This means the liquid methane itself is not pure. It is a solvent enriched with this tholin material, creating a nutrient-rich broth in which further chemistry could occur. So, while the subsurface ocean represents a potential habitat for water-based life, the surface presents a parallel possibility. The methane seas are not empty. They are infused with this tholin material, a concentrated source of complex organic molecules. An azotosome, a self-assembled membrane drifting in the Kraken Mare, would be floating in a solution teeming with potential chemical fuel. The tholins could provide the raw materials for metabolic reactions, offering a source of energy and carbon for any hypothetical life form that could learn to exploit it. It's a scenario that turns our understanding of habitability on its head. We often think of a habitable world as one that is clean and temperate like Earth. But Titan suggests that a habitable world might actually be a messy one, a place that is actively cooking complex chemistry on a global scale, painting its entire surface with the rusty hues of prebiotic possibility. This constant, slow rain of organic matter means the ingredients for complexity are not just present. They are being delivered season after eon, building up a deep reservoir of potential right on the moon's doorstep. Yet, for all the fascinating possibilities on the surface, the environment that may hold the greatest promise for life as we might recognize it lies sealed away beneath the ice in that global subsurface ocean. It's a realm of profound extremes, a water world existing in perpetual midnight under a crushing blanket of ice and pressure. But what exactly would this hidden sea be made of? It is almost certainly not a pristine freshwater ocean. Instead, the clues point toward something far more intriguing. A dense, salty brine, a chemical soup with a composition that could make it a potent cradle for prebiotic chemistry. This isn't the clear blue water of Earth's tropics. It's more akin to the densest, saltiest waters found at the bottom of our own seas, or even to the extremely salty lakes like the Dead Sea. The salts dissolved within it are thought to be similar to those found on Earth compounds like sodium chloride, magnesium sulfate, and various carbonates, but they might be present in much higher concentrations, creating a solution that remains liquid at temperatures far below the normal freezing point of water. This briny nature is the key to its very existence, acting as a powerful antifreeze that prevents the entire ocean from turning into a solid block of ice. The source of this salinity is as fundamental as the ocean itself. The ocean is not just sitting in an empty cavern, it is in direct contact with Titan's rocky, silicate core. This core, heated by the decay of radioactive elements, is likely similar in composition to the rocky bodies of the inner solar system. And just as seawater on Earth reacts with the ocean floor, leaching out minerals, Titan's ocean is probably slowly dissolving elements from its rocky bed. Over billions of years, this process would have transferred a significant portion of the core's soluble minerals into the water, creating the salty brine we infer today. But this interaction between water and rock is far from a passive, slow dissolution. It is the engine for what could be the most biologically promising environment on all of Titan, hydrothermal systems. On Earth, we discovered a whole new way life can exist when we found vast ecosystems thriving in the absolute darkness of the deep ocean, clustered around hydrothermal vents. These are essentially underwater geysers where seawater seeps down into cracks in the ocean crust, is superheated by the Earth's internal magma, and then spews back out, rich with dissolved minerals like hydrogen sulfide and metals. The water can reach temperatures of hundreds of degrees, yet it doesn't boil because of the immense pressure. This heated, mineral-rich fluid provides both the energy and the chemical building blocks for bacteria, which in turn support entire food webs of tube worms, clams, and crabs, all independent of sunlight. The entire system runs on chemosynthesis, using chemical energy instead of solar energy. Now, translate that concept to the ocean floor of Titan. We have a warm, rocky core. We have a global ocean of liquid water sitting right on top of it. The physics are virtually identical. It is overwhelmingly likely that hydrothermal vent systems are active on Titan's seafloor. Water would be circulating through the rocky core, being warmed, and erupting back into the ocean, carrying a cocktail of dissolved minerals. The specific chemistry would be different from Earth's, perhaps richer in certain compounds like ammonia or different sulfur species, but the fundamental principle is the same: a constant, localized source of energy and chemical gradients. This is not merely a hospitable place, it is a driving force for chemistry. The interface between the hot, mineral-laden vent fluid and the cold, dense brine of the ocean proper creates a dynamic environment where molecules are encouraged to link up to form more complex structures. It's in such environments that many scientists believe the very first steps toward life on Earth may have occurred. The vents provide order out of chaos, a focused stream of energy that can power the formation of increasingly complex organic molecules. So, while the surface of Titan offers a vision of a truly alien, hydrocarbon-based biology, its hidden ocean presents a parallel narrative that feels hauntingly familiar. It is a dark, high-pressure world, but one where the same geochemical processes that might have sparked life on our own planet could be unfolding right now, a billion miles away. This ocean has been isolated, evolving in its own way for perhaps the entire history of the solar system, sealed beneath an ice shell that protects it from the harsh radiation and exotic chemistry of the surface. It is a pristine laboratory, a time capsule that might hold clues to how life begins in water, under conditions that could be common on icy worlds throughout the galaxy. The potential for two completely independent paths to life on a single world, one in water, one in methane, makes Titan not just a candidate for habitability, but a symbol of the universe's astonishing versatility. So, with all these complex molecules and potential cellular structures, we arrive at the ultimate question: what would power it all? For any form of life, energy is the non-negotiable currency. On our sun-drenched planet, the ultimate source for nearly every ecosystem is photosynthesis, capturing solar energy. But Titan's surface is a dim, cold place, and its subsurface ocean is a world of absolute darkness. If life exists in either realm, it would have to follow a completely different economic model, one based entirely on chemical energy. The good news is that Titan appears to be a place brimming with such potential, offering different menus of energy sources for its two isolated environments. Let's start on the surface in the hydrocarbon seas. Here, the sun's light is a faint, diluted glow, far too weak to power anything like earthly photosynthesis. But the atmosphere itself may be generating a different kind of fuel. Scientists analyzing data from the Cassini mission noticed something intriguing about the chemistry on Titan's surface. The atmosphere is constantly producing a molecule called acetylene. When acetylene falls to the surface and dissolves in the liquid methane seas, it could meet another simple but powerful agent, molecular hydrogen. Hydrogen is lighter than Titan's thick nitrogen atmosphere and should, in theory, be slowly escaping into space. Yet, Cassini's instruments detected a surprising amount of it at the surface level, suggesting it's being replenished from below, perhaps seeping up from the interior. This sets the stage for a fundamental chemical reaction. When acetylene and hydrogen come together in the presence of a suitable catalyst, perhaps a mineral on the seafloor, they can react to form methane. This reaction releases energy. It's an exothermic process. On Earth, we burn acetylene in torches for a high-temperature flame. On Titan, the reaction would be much slower due to the cold, but it would still represent a steady, accessible source of chemical power. For a hypothetical methane-based life form, this could be its version of eating. An organism might have evolved a way to catalyze this reaction, harnessing the released energy to build more complex molecules and sustain its metabolism. It would be a form of chemosynthesis, but one entirely divorced from water, using the very hydrocarbons that make up its world as both solvent and fuel. Essentially, these life forms would be consuming a chemical gradient, the difference between the abundant acetylene on the surface and the hydrogen seeping up from below, turning it into a usable energy source in the eternal twilight. But the real powerhouse for life might lie deep below in the hidden ocean. Cut off from the sun and the surface's organic haze, any biology here would need to tap into the moon's internal heat. And Titan's warm, rocky core offers two particularly promising ways to do just that, both of which have parallels right here on Earth. The first is a process called radiolysis. Remember, Titan's core is heated by the decay of radioactive elements like uranium and thorium. As these elements break down, they emit radiation. When this radiation passes through the water of the subsurface ocean, it can smash water molecules apart, producing molecular hydrogen and highly reactive oxidants like hydrogen peroxide. This might sound destructive, but it's actually a tremendous gift to chemistry. It creates a classic energy source, a redox gradient. The hydrogen is a reducing agent, eager to donate electrons, and the oxidants are, as the name implies, eager to accept them. When they meet and react, energy is released. On Earth, we find microbes living deep underground in isolated water pockets, surviving for millions of years solely on the energy provided by radiolysis. Titan's ocean, bathed in this gentle, persistent radiation for billions of years, could be teeming with such chemical potential, offering a ubiquitous, if low-level, energy source throughout its vast volume. The second, and perhaps even more compelling, energy source is tied directly to the interaction between the ocean and the rocky core, a process known as serpentinization. This occurs when water interacts with certain iron and magnesium-rich minerals in the rock, like olivine. The reaction alters the rock, turning it into a new family of minerals called serpentines. But more importantly for life, this geochemical process has two crucial byproducts. First, it releases a substantial amount of heat, further helping to keep the ocean liquid. Second, and most significantly, it produces molecular hydrogen and creates a highly alkaline environment. This hydrogen, just like from radiolysis, is a potent fuel. But serpentinization does more. It can also lead to the formation of simple organic molecules like methane and more complex hydrocarbons. This is a one-stop shop for prebiotic chemistry. It provides heat, a rich energy source in the form of hydrogen, and the basic building blocks for organic compounds. This is not just theoretical. On Earth, we see the results of this process at Lost City, a spectacular hydrothermal vent field in the Atlantic Ocean. Unlike the black smoker vents that belch superheated, mineral-rich smoke, Lost City vents are cooler and are driven by serpentinization reactions. They create towering, ghostly white carbonate chimneys that seep warm, alkaline fluid rich in hydrogen and methane. And these vents are surrounded by lush microbial ecosystems that thrive on this chemical bounty. The conditions at Lost City are considered one of the most promising models for where life might have originated on Earth. On Titan, where the ocean is in direct contact with a similar rocky core, it is almost a certainty that serpentinization is occurring. This means the ocean floor could be dotted with hydrothermal systems akin to Lost City, creating oases of chemical energy and complexity in the abyssal dark. These vents would provide not only the fuel but also the mineral surfaces and dynamic conditions that could encourage molecules to organize and react, potentially taking the critical steps from chemistry toward biology. So, while the surface offers a bizarre, alien energy pathway, the subsurface ocean presents a scenario that feels deeply familiar to our own planet's history, suggesting that the recipe for life might be a universal one, waiting only for the right kitchen to prepare it in. This thick global layer of ice, then, becomes far more than just a shell. It is a central character in Titan's story, acting as both a formidable barrier and a potential, albeit fragile, bridge. For billions of years, it has likely maintained a strict segregation between the two radically different chemical kitchens we've explored: the warm, dark, water-based ocean below and the cold, complex, hydrocarbon-soaked surface above. This separation is crucial. It would allow any potential biology in the ocean to evolve in isolation, protected from the exotic and possibly destructive chemistry of the surface, and vice versa. They could be two independent experiments in the origins of life, running in parallel without ever interfering with each other. The ice acts as a cosmic insulator, a lid on a pot that has been simmering on its own for eons. But what if that lid isn't as sealed as we think? What if, every so often, the internal pressures and heat of Titan find a weak spot in this icy armor, creating a temporary passageway? This is where one of the most dynamic and fascinating geological processes in the outer solar system comes into play: cryovolcanism, or ice volcanism. On Earth, volcanoes spew molten rock. On Titan, a cryovolcano would erupt with a very different kind of lava: a slushy, semi-liquid mixture of water ice, ammonia, salts, and perhaps even material from the deep ocean itself. Think of it not as a fiery mountain, but as a slow, oozing fountain of relatively warm ice welling up from the depths below. The mechanics behind this are driven by Titan's internal heat. The warmth from the radioactive core doesn't just keep the ocean liquid, it also creates convection currents within the ocean and the overlying ice shell. Warmer, buoyant plumes of water can rise towards the underside of the crust, much like hot magma rises in Earth's mantle. If such a plume is powerful enough and finds a crack or a thin spot in the ice, it could push its way upward. The mixture of water, ammonia, which acts as a powerful antifreeze, and dissolved salts would be less dense than the surrounding solid ice. This allows it to intrude into the crust, potentially all the way to the surface, where it would erupt or slowly extrude, freezing into unique geological formations, cryovolcanic domes, and flows that would look very different from the impact craters and fluvial valleys elsewhere on Titan. While definitive evidence of active cryovolcanism on Titan is still being debated, several intriguing features spotted by the Cassini radar look like strong candidates. There are domes and flows with a peculiar geological signature that don't match simple water ice, suggesting they are made of a different mixture of materials. If these are indeed cryovolcanos, their implications are staggering. They would be a mechanism for transferring material from the hidden ocean to the surface. A cryovolcanic eruption wouldn't just bring up water. It could carry a rich cocktail of dissolved salts, complex organic molecules that may have formed in the ocean, and in the most thrilling scenario, even potential biomarkers or microbial life itself, if it exists down there. Imagine this process. A deep-sea vent community thrives in the darkness of the subsurface ocean, sustained by chemical energy. Then, a geological event triggers an uprising of warm water, which carries some of these organisms or their complex chemical products upward through a fissure in the ice. Over time, this material is transported through dozens of miles of crust, eventually being deposited onto the frigid surface. There, it would freeze solid, embedded in a new landscape of water ice and snow, and be exposed to the entirely different environment of Titan's surface, the liquid methane, the tholin rain, the cosmic radiation. For an organism adapted to the warm, dark, high-pressure ocean, this would almost certainly be a death sentence, but its complex organic remains, its chemical fingerprints, would now be present on the surface. This creates a phenomenal opportunity for future exploration. A lander wouldn't necessarily need to drill through the ice shell to see what's in the ocean. It could simply visit a suspected cryovolcanic site and analyze the freshly erupted material. It would be like sampling the deep ocean without ever having to dive. The ice shell, therefore, transforms from an impenetrable barrier into a possible conveyor belt, a geological system that might occasionally shuffle the deck between the two worlds. It raises the profound, almost poetic possibility that the ingredients for life forged in the alien water below could be sprinkled onto the alien landscape above, offering them a chance to interact with the hydrocarbon-based chemistry there. While the two biospheres would likely remain independent, cryovolcanism suggests they might not be entirely strangers, but distant relatives who occasionally exchange gifts across a frozen, cosmic frontier. Now, let's focus our attention on one of the most tangible possibilities for life in that hidden ocean, the seafloor itself. This isn't just a flat, barren plain. Given the heat flowing from Titan's warm, rocky core, it is almost a certainty that the ocean floor is punctuated by hydrothermal vent systems, geological features that on Earth are not just fascinating, they are veritable cradles of life. The concept is as elegant as it is powerful. On our own planet, these vents form where seawater percolates down through cracks in the oceanic crust, gets superheated by magma close to the Earth's core, and then erupts back into the cold, deep ocean. This creates a turbulent, mineral-rich environment, a stark contrast between the scalding, chemical-laden vent fluid and the frigid surrounding water. That contrast, that gradient, is a potent source of energy, and it's precisely this kind of environment that many scientists believe could have provided the spark for the very first life on Earth. On Titan, the fundamental geology is strikingly similar. A liquid water ocean sits in direct contact with a silicate rock core. Heat from the decay of radioactive elements within that core provides the engine. The only missing ingredient for a hydrothermal system is circulation, and with a whole ocean pressing down, it's difficult to imagine that not occurring. The type of vent system that might be most relevant for Titan is a specific class known as serpentinization vents. This process has nothing to do with fiery magma. Instead, it's a quieter, more pervasive geochemical reaction between water and certain minerals in the rock, particularly olivine. When water interacts with these iron and magnesium-rich rocks, it transforms them into a new family of minerals called serpentines. But the magic of serpentinization lies in its byproducts, The reaction is exothermic, meaning it releases heat, which further helps sustain the ocean's liquid state. More importantly, it produces two crucial substances, vast quantities of molecular hydrogen and a highly alkaline or basic fluid. The hydrogen gas is a powerful reducing agent, a molecule eager to donate electrons. This sets the stage for a fundamental energy-generating process. On Earth, we have a spectacular example of this in the Lost City hydrothermal field, located in the Atlantic Ocean. Unlike the so-called black smoker vents that belch dark, superheated, metal-rich smoke, Lost City features towering, ghostly white carbonate chimneys that vent warm, alkaline fluid rich in hydrogen and methane. These structures are not barren. They are teeming with microbial life that thrives by metabolizing the hydrogen, using it to convert carbon dioxide and other compounds into energy. If we transplant this concept to Titan's ocean floor, the implications are profound. A lost city-like environment on Titan would provide a continuous and long-lived source of both chemical energy and potential building blocks. The hydrogen gas is the fuel, but the process can also generate simple organic molecules like methane and formate, which are the basic starting points for more complex chemistry. The mineral surfaces of the vent chimneys themselves could act as catalysts, providing a scaffolding upon which these simple molecules could assemble into more complex chains, perhaps even the precursors to proteins and genetic material. It's a self-contained chemical factory operating in complete darkness, independent of any energy from the sun. The duration of this activity is key. While volcanic activity might be sporadic, serpentinization can continue for tens of thousands, even millions of years, offering a remarkably stable environment for chemistry to experiment and complexify over immense stretches of time. What makes this parallel so compelling is that it suggests a potential path to life that is not alien or bizarre, but one that could be a universal rule. The conditions that led to life on Earth, liquid water, a rocky seabed, and chemical energy from water-rock interactions, are not unique to our world. They appear to be replicated on Titan and likely on other icy moons like Europa and Enceladus. This means the recipe for life might be a common one throughout the cosmos, requiring only a few fundamental ingredients that are themselves commonplace. The hydrothermal vents on Titan's ocean floor represent more than just a hopeful habitat. They are a test of a fundamental hypothesis about the origin of life itself. If we were to one day discover that life exists there, it would powerfully suggest that wherever you find water, rock, and a source of energy, life may not be a rare miracle, but an almost inevitable chemical consequence. This profound cold, however, presents what might be the single greatest challenge to the emergence of life on Titan's surface. We are talking about temperatures so low that they redefine the very pace of existence. At nearly 300 degrees below 0 Fahrenheit, the frantic dance of molecules that drives all chemistry on Earth slows to a glacial crawl. Heat is energy, and in this deep freeze, there is simply very little thermal energy available to kickstart and sustain the complex reactions that life requires. A molecule that might spontaneously react in a fraction of a second in the warm waters of Earth could take years or even centuries to find the necessary energy to undergo the same transformation in a Titanian methane sea. This isn't just a minor obstacle, it's a fundamental barrier that seems to push the very idea of life into the realm of fantasy. But nature is a master of adaptation, and the rules of chemistry are not absolute, they are a spectrum of possibilities. While heat speeds things up, it is not the only way to facilitate a reaction. This is where the concept of catalysts becomes paramount. A catalyst is a substance that lowers the energy barrier required for a reaction to occur, allowing it to proceed at a much faster rate without the catalyst itself being consumed. In our own bodies, enzymes are biological catalysts that make life possible at a speed we recognize. For a hypothetical life form on Titan, evolution would have had to discover or invent catalysts uniquely suited to the cryogenic environment. These wouldn't be protein-based enzymes like ours, which would instantly freeze and become useless. Instead, they might be based on different elements altogether, perhaps metals like titanium or zirconium that can function as effective catalysts even at incredibly low temperatures, or they could be complex organic structures shaped by the unique chemistry of tholins. The very surface of Titan might be peppered with mineral catalysts that could have served as the initial templates for a slower, colder kind of biochemistry. This leads to a truly mind-bending possibility: the pace of life itself. If the underlying chemical reactions are orders of magnitude slower, then any biological processes would be correspondingly decelerated. Imagine an organism for whom a single metabolic cycle, the equivalent of digesting a meal, takes not hours but decades. Its heart, if it had one, might beat once a year. Its thoughts, if it could think, would unfold over centuries. 1,000 Earth years might pass as nothing more than a long summer in the lifespan of such a being. Their entire civilization, from its dawn to its eventual decline, could span millions of our years, unfolding at a tempo we would perceive as a standstill. This isn't about life being sluggish or inefficient. It's about life existing on a different timescale altogether, one that is perfectly synchronized with the slow, patient chemistry of its world. For them, our frenetic, sun-warmed lives would seem like a frantic, blinding flash. This concept forces us to confront our own temporal chauvinism. We are prisoners of our experience, conditioned by the rapid rhythm of a warm, energy-rich planet. We instinctively search for life that operates on a human timescale, but the universe is under no obligation to conform to our expectations. On a world like Titan, life wouldn't be struggling against the cold. It would be exquisitely adapted to it, its very slowness being the key to its stability and success. The low-energy environment would prevent damaging side reactions, allowing for a level of precision and durability we can scarcely imagine. While we might initially see such existence as a form of suspended animation, it could represent a profound and valid alternative pathway for biology, one of immense patience and longevity, a quiet, persistent whisper of life in the vast and silent cold. This brings us to one of the most profound puzzles in our search for alien biology: the molecule of inheritance. On Earth, the blueprint for every known living thing is written in the elegant, double-stranded code of DNA. It's a masterpiece of evolution, but it is also a molecule exquisitely tailored to our planet's warm, watery environment. On Titan, where temperatures are hundreds of degrees colder, and the solvent might be liquid methane instead of water, DNA as we know it would be utterly useless. Its intricate helical structure would likely shatter or become inert in the cryogenic cold, and its components might not even dissolve in a hydrocarbon sea. So, if life exists there, what molecule could possibly carry the torch of heredity, storing and transmitting information in such an alien setting? The fundamental job of a genetic molecule isn't tied to a specific chemical structure. Its core functions are to store information in a stable way, to be able to replicate that information faithfully, and to allow for occasional mistakes, mutations, that provide the raw material for evolution. DNA performs these tasks brilliantly on Earth, but the universe of chemistry is vast. Scientists have begun to explore alternative molecules that could, in theory, fulfill these same roles under different conditions. One of the most compelling candidates is a substance known as peptide nucleic acid, or DNA. Imagine a molecule that mimics the shape of DNA but is built from a completely different backbone. Instead of the sugar phosphate spine that defines DNA, PNA uses a backbone of linked peptides similar to the structure of proteins. This simple change has revolutionary implications. A PNA backbone is electrically neutral and is far more chemically stable than DNA. It's less prone to breaking down and, crucially, it can form stable double helices at a much wider range of temperatures, including the extreme cold found on Titan. It wouldn't rely on the hydrogen bonds that hold DNA together, which are weak and temperature sensitive, but on the stronger, more robust forces of its own structure. But DNA is just one possibility in a cosmos of potential genetic molecules. Another intriguing idea is that Titanian life might not use a single, elegant double helix at all. Instead, its genetic information could be stored in a system of interlocking mineral-based crystals. Certain crystals, as they grow, can trap imperfections or impurities within their orderly atomic lattices. These imperfections can, in a sense, encode information. While this might sound like science fiction, it's a concept that has been seriously proposed as a potential pathway for very simple, non-biological information transfer. A more plausible alternative for a complex biology, however, could be an information system based on something other than a linear chain. Perhaps heredity on Titan is managed by complex three-dimensional networks of molecules where information is stored not in a sequence of bases, but in the specific branching patterns and connection points of a vast organic polymer, something akin to the Tholen material that already coats the Moon. The very process of replication would have to be fundamentally different. On Earth, replication is a fast, dynamic process driven by the thermal energy of our environment. Enzymes zip along the DNA strand, quickly assembling a new partner. On Titan, that kind of speed is impossible. Replication would be a slow, deliberate, almost geological process. It might rely on templating, where a molecule slowly aligns complementary building blocks next to itself, not with enzymatic help, but through the patient, passive forces of molecular attraction in the viscous liquid methane. A single act of cell division might take years or even centuries. This glacial pace would have cascading effects on the entire tempo of evolution. While mutation rates might be lower due to reduced background radiation and slower chemistry, the time between generations would be astronomically long. Evolution on Titan wouldn't be a race, it would be an immensely patient, slow-motion dance, where successful adaptations could take millions of our years to become established in a population. This leads to a staggering thought about the nature of such life. If Titanian organisms have indeed arisen, they would be so perfectly synchronized with their slow-motion world that our own rapid existence would be incomprehensible to them. Their perception of time, their metabolism, their very consciousness, if it exists, would be calibrated to a clock that ticks once for every 1,000 of our ticks. They would experience a single Titanian year, which is equivalent to 29 Earth years as a normal annual cycle. A solar day on Titan lasts 16 Earth days. Their daily rhythm of activity and rest would span our weeks. For beings living in the subsurface ocean, where the concept of day and night is meaningless, their rhythms would be tied entirely to the slow pulses of geothermal energy from the core. A civilization of such beings, should one exist, would plan its projects on a millennial scale, its history unfolding over epochs that dwarf all of human history. Their art, their science, their very philosophy would be built upon a foundation of immense patience, a perspective on the universe that we, with our fleeting, frantic lives, can barely conceptualize. They are a testament to the idea that life is not a single phenomenon, but a spectrum of possibilities, each perfectly adapted to the rhythm of its own world. Given the incredible possibilities we have been exploring, it becomes clear that to move from speculation to discovery, we need to return to this alien world with new eyes and more capable tools. Our current understanding is built on the shoulders of a monumental mission that gave us our first real glimpse of Titan's surface. The Cassini-Huygens mission, a collaboration between NASA and the European Space Agency, was a game-changer. For 13 years, the Cassini orbiter circled Saturn, performing over 100 flybys of Titan. Its radar pierced the thick haze, mapping the surface and revealing the lakes and seas we now know so well. But the most dramatic moment came in 2005, when the Huygens probe, which had hitched a ride with Cassini, detached and began its 2.5-hour descent through the opaque atmosphere. No one knew what it would find. Would it splash down into a global methane ocean or land on something solid? The images that came back were breathtaking. We saw a landscape of rounded ice pebbles carved by fluid flow, set against a hazy orange sky. Huygens had landed on a dry riverbed, a snapshot of a dynamic world, and it transmitted data from the surface for over an hour, forever changing our view of this moon from a featureless orb to a complex geological wonder. The legacy of that mission is immense, but it also left us with burning questions. Cassini's radar could see the shapes of the lakes, but it couldn't analyze their chemical composition in fine detail. Huygens gave us a single, spectacular snapshot from one location, like looking at one grain of sand on an entire beach. We learned that the ingredients for prebiotic chemistry are there, but we have no idea if they are actually combining into anything more complex. We know there is a subsurface ocean, but we have no direct samples from it. The mission was a brilliant reconnaissance that unveiled the stage, but the actual chemical processes that might be unfolding remains a mystery. To solve it, we need a mission that can explore Titan with the mobility and precision that a stationary lander simply cannot provide. This is precisely the goal of one of the most ambitious robotic explorers ever conceived, Dragonfly. Scheduled to launch in 2028 and arrive in the mid-2030s, Dragonfly is not a rover or a lander, but a nuclear-powered drone rotorcraft. Think of it as a large, sophisticated drone designed to fly through Titan's thick atmosphere, which, combined with the moon's low gravity, makes it an ideal world for flight. Dragonfly will land initially in the equatorial region among the vast dunes of organic sand, but its true power is its ability to travel. Over a planned mission of nearly 3 years, this rotorcraft will make dozens of flights, hopping tens of kilometers at a time to explore a variety of environments, from the dune fields to the floor of an impact crater. This mobility is crucial because it allows scientists to not just study one spot, but to compare different locations to see how the organic chemistry varies from the dry dunes to an area where liquid water may have once mixed with surface organics in a past impact event. Dragonfly's suite of instruments is our astrobiologist's dream, designed specifically to hunt for the building blocks of life. It will carry a mass spectrometer to identify complex organic molecules in the atmosphere and on the ground. A gamma-ray and neutron spectrometer will analyze the elemental composition of the surface, telling us exactly what the sand dunes are made of. Most importantly, it can even drill a small sample of surface material and analyze it inside its onboard laboratory, protected from the extreme cold. Dragonfly will be looking for those key prebiotic molecules we've discussed: amino acids, nucleotide bases, and the complex chains of tholins. But it will go further, seeking evidence of chemical processes that could indicate energy sources for life, such as the depletion of acetylene or hydrogen at the surface, which would be a tantalizing sign that something might be consuming it. The potential discoveries are staggering. Dragonfly could effectively ground truth our theories about azotosomes by searching for the specific molecules that form them. It could analyze the tholin-rich dunes to see just how complex this organic material has become over billions of years. By visiting an impact crater, it might find evidence of what happens when water from a subsurface ocean briefly interacts with surface organics, a process that could mimic the conditions of early Earth. Each flight will be a journey to a new laboratory, offering a chance to see if Titan's chemistry is stagnant or actively progressing toward greater complexity. This mission represents a quantum leap in our exploration of the outer solar system. It moves us from passive observation to active, targeted investigation of a world that challenges our very definitions of habitability. Dragonfly won't just be visiting a moon. It will be conducting a field study in an alien chemical environment, with the potential to tell us whether the steps toward life are a unique earthly recipe or a common, universal phenomenon waiting to be uncovered on worlds we are only beginning to understand. Settling into the Shangri-La dune fields, Dragonfly's first task will be to understand the fundamental ingredients that have been accumulating here for perhaps billions of years. This isn't just sand in the earthly sense. These vast, wind-sculpted dunes are likely made of granules of water ice, but coated and darkened by that continuous rain of complex organic tholins. Think of it as a sprawling field of frozen sand grains, each one encased in a layer of prebiotic goo. Dragonfly's gamma-ray and neutron spectrometer will act like a cosmic X-ray machine, peering into the composition of the ground beneath it to determine the exact mix of elements present. How much carbon, hydrogen, nitrogen, and oxygen is locked away in this organic repository. But the real magic happens when it deploys its drill. By collecting a small sample of this dune material and feeding it into its onboard mass spectrometer, the lander will be able to perform a detailed chemical census. It won't just confirm the presence of complex molecules, it will identify them with stunning precision, looking for the specific building blocks we associate with life, such as amino acids and the nucleobases that form the information-carrying backbone of DNA and RNA. This is like being handed a recipe book from another world. We'll be able to see not just that the ingredients are there, but how complex they have become simply through atmospheric and surface processes without any biology required. The journey from the dunes to the Selk impact crater is where the mission's true investigative power comes into play. Selk is not just a random hole in the ground. It is a chosen destination because it represents a place where Titan's two potential kitchens for life may have briefly interacted. When a large object strikes Titan's surface, the immense energy of the impact can melt through the icy crust, creating a temporary pool of liquid water that might last for hundreds or even thousands of years before refreezing. This creates a phenomenal natural experiment. For that period, the complex organic tholins on the surface would have been mixed and heated in a watery environment, a scenario that closely mimics the conditions thought to have sparked life on the early Earth. By flying to Selk, Dragonfly can sample the material on the crater floor, searching for the chemical fingerprints of this ancient mixing event. Did the water and organics react to form even more complex molecules like peptides or lipids? The instruments on board are designed to detect the chemical pathways that such reactions would have taken, offering a glimpse into a process that could be a critical step toward biology, frozen in time for our inspection. Beyond simply cataloging molecules, Dragonfly has a more subtle and profound objective: to listen to the chemical heartbeat of Titan and see if anything is actively consuming energy. One of the most tantalizing experiments it can perform is to monitor the atmosphere and soil for signs of metabolic waste. On Earth, if you were to measure the air and soil around a thriving ecosystem, you would find imbalances. Certain gases would be depleted because living things are breathing them in, while others would be enriched as waste products. Dragonfly will be looking for similar chemical gradients. A key target will be hydrogen gas. We know hydrogen is produced in the atmosphere and should be drifting down to the surface. If Dragonfly finds that the hydrogen concentration at the surface is significantly lower than models predict, it could be a powerful, albeit indirect, indicator that something on the surface is consuming it as a food source. Similarly, it will look for the depletion of acetylene, another potential energy source we discussed. It's a search for a shadow biosphere, not by looking for life itself, but by detecting the vacuum it might leave in the chemical buffet around it. A lack of these expected chemicals would be a quiet but revolutionary finding, suggesting that Titan's chemistry is not passive but is being actively manipulated. Ultimately, every sample analyzed and every atmospheric reading taken contributes to Dragonfly's primary goal: to assess the actual habitability of Titan's environment today. This goes beyond the simple question of whether the ingredients for life are present. It asks whether those ingredients are accessible and can be used in a sustained way. Are the energy sources we've identified, like the acetylene-hydrogen reaction, actually feasible at Titan's surface temperatures? Are the building blocks like amino acids stable, or do they break down too quickly? By acting as a mobile field laboratory, Dragonfly will provide the ground truth data needed to move our understanding of Titan from a world of fascinating potential to a world with a quantified, understood potential for prebiotic chemistry or even biology. It will tell us if Titan is merely a museum of complex organic molecules, a beautiful but static display of what chemistry can do, or if it is an active, dynamic kitchen where the recipes for life are still being written and experimented with even now. But after Dragonfly has scoured the dunes and craters, after it has mapped the complex organic chemistry of the surface, the ultimate question will remain: how would we actually recognize life if we found it? We can't simply look for squirrels or fish. We need to search for the subtle, chemical whispers of biology, for what scientists call biosignatures. These are not the life forms themselves, but the detectable traces they leave behind in their environment. The fingerprints of a metabolic process, the waste products of existence, the chemical shadows cast by living systems. And on a world as dualistic as Titan, the search for these signatures splits into two parallel investigations, each with its own set of clues and profound challenges. On the surface, within the frigid methane seas and tholin-coated landscapes, the hunt would focus on detecting an imbalance. A world without life tends toward chemical equilibrium. Gases and compounds eventually reach a stable, predictable distribution. But life is a fundamentally disruptive force. It consumes specific resources and expels specific waste, creating pockets of disequilibrium. One of the most promising biosignatures for Titan's surface would be a surprising depletion of key atmospheric gases. As we discussed, acetylene and hydrogen are potential food sources. If a lander like Dragonfly were to find that the concentration of hydrogen at the surface is dramatically lower than models predict, or that acetylene is strangely absent from the soils around the methane lakes, it would be a powerful, albeit indirect, hint that something is actively consuming them. It would be like arriving at a banquet and finding that one particular dish has been completely cleaned out, suggesting there were hungry guests we simply haven't seen yet. Furthermore, we would search for an excess of the expected waste products. If something is metabolizing acetylene and hydrogen to produce methane, we might look for an unexplained enrichment of methane in localized areas. The signature wouldn't be a single molecule, but a pattern, a specific and unexpected ratio of chemicals that defies non-biological explanations. Beyond gas imbalances, we would look for a different kind of complexity in the molecular soup. The tholins that rain down on Titan are complex, but their complexity is random, a chaotic mixture of chains and rings formed by the indiscriminate energy of sunlight. Biology, in contrast, is highly selective. It favors specific molecules and assembles them in non-random, repeating patterns. A key biosignature would be the discovery of a surprising homochirality. Many complex organic molecules, including the amino acids that are the building blocks of proteins, come in two mirror image forms like a left and a right hand. Non-biological processes produce a roughly 50-50 mix of both, but life on Earth uses almost exclusively the left-handed versions of amino acids. This specific preference is a hallmark of biology. If we were to find that the amino acids on Titan's surface show a strong preference for one hand over the other, it would be one of the most compelling signs imaginable that a selective biological process has been at work, sorting and organizing the building blocks. We would also search for molecules of a specific size and function, like lipids that could form azotosome membranes, arranged in ways that suggest they are part of a structured system, not just a random chemical sludge. But what of the hidden ocean? Detecting biosignatures, their presence a far greater technological hurdle, as it requires penetrating the icy shell, but the potential signatures might be more familiar to us. A future probe, perhaps a cryobot that melts its way down through the ice, would enter a water-based environment. There, it would look for clues similar to those we find in Earth's most isolated aquatic ecosystems. One of the strongest biosignatures would be the detection of chemical gradients around potential hydrothermal vents. The probe's sensors would look for sharp changes in temperature, acidity, and concentrations of compounds like hydrogen sulfide or methane emanating from the seafloor. While such gradients can form abiotically if they are accompanied by a dramatic increase in the concentration and complexity of organic molecules, a soup of life's building blocks that gets richer as you approach the vent, it would strongly suggest a biological community is present, concentrating and utilizing these resources. Perhaps the most exciting method would be to search for specific patterns in the organic molecules themselves. On Earth, sophisticated instruments can analyze a sample of seawater and detect the spectral fingerprints of complex pigments like chlorophyll, or the distinct patterns of molecules like certain lipids that are almost exclusively produced by living organisms. A probe in Titan's ocean could use similar techniques, scanning the water for the unique chemical signatures of complex polymers or information-carrying molecules. Finding a molecule that acts as a hereditary material, even if it's not DNA, would be the ultimate discovery. Its structure would likely show a repeating, information-rich pattern, a non-random sequence that screams of biological function. The biosignature wouldn't just be the molecule's presence, but its intricate, coded architecture. Ultimately, the search for life on Titan is a search for a pattern that cannot be easily explained by geology or chemistry alone. It is the hunt for a signal of complexity, selectivity, and energy utilization that defies the passive tendencies of a sterile world. Whether it's the suspicious absence of a gas on the surface or the telltale molecular fingerprint of a metabolic process in the deep ocean, a confirmed biosignature would tell us one thing: we are not alone in the universe, and the recipe for life is not a single, fragile formula, but a universal cookbook with many different, equally valid pages. But as we marvel at the possibilities within Titan's hidden sea, it's crucial to understand that this moon is not a solitary anomaly. It is part of a remarkable family of worlds now known as ocean worlds, each with its own unique recipe of ice, water, and potential. To truly appreciate Titan's place in this cosmic lineup, we need to compare it with its two most famous siblings, Jupiter's moon Europa and Saturn's own Enceladus. While they all share the breathtaking feature of a subsurface ocean, the differences in their construction create vastly different environments and consequently vastly different prospects for life. Let's begin with Enceladus, the smallest of the three but arguably the most dramatic. This tiny, gleaming moon is only about 300 miles across, yet it boasts one of the most active landscapes in the solar system. During its mission, the Cassini spacecraft made an astonishing discovery: gigantic plumes of water vapor and ice crystals erupting from a series of fractures near its south pole, spewing material hundreds of miles into space. This was our direct, undeniable proof that not only does Enceladus have a subsurface ocean, but that this ocean is actively venting its contents into the void. This changes everything for exploration. We didn't need to land or drill. Cassini simply flew through these plumes and analyzed their composition. It found that Enceladus's ocean is salty, contains a variety of simple organic molecules, and is likely in contact with a rocky hydrothermal seafloor. The entire system is like a geyser, offering us a free sample of its deep ocean. However, this very activity points to a key difference from Titan. Enceladus's ice shell is thought to be relatively thin, perhaps only 20 to 30 miles thick in places. This thinner shell is more susceptible to the gravitational tug of war with Saturn, creating friction and heat that helps keep the ocean liquid and allows for these spectacular eruptions. But this thinner shell also means less protection from radiation and cosmic impacts, and it suggests the ocean might be younger or more transient than Titan's. Then there is Europa, a world that sits somewhere between the extremes of Enceladus and Titan. Slightly smaller than our own moon, Europa's surface is a breathtaking mosaic of cracked and jumbled ice, resembling a celestial cracked egg. Its ocean is believed to be immense, containing perhaps twice the volume of all Earth's oceans combined, and it is shielded by an ice shell that is thicker than Enceladus's but significantly thinner than Titan's, estimated to be 10 to 20 miles deep. Unlike Enceladus, Europa does not have persistent globe-spanning plumes, though there is evidence of occasional water vapor venting. Its primary energy source is different as well. While it likely has hydrothermal activity on its seafloor, the main heat keeping its ocean liquid comes from tidal flexing caused by Jupiter's immense gravity, which constantly kneads and stresses the moon's interior. This creates a world with a vast, potentially ancient ocean, but one that is arguably more difficult to sample directly than Enceladus's and less shielded than Titan's. This is where Titan's unique profile comes into sharp focus. Its subsurface ocean is the grandest in scale, potentially reaching depths of 50 to 100 miles, dwarfing the others in sheer volume. But the most significant distinction is its incredible insulation. Titan's ice shell is a behemoth, estimated to be 60 to 80 miles thick. This is a colossal lid, a barrier of immense strength and depth that has likely sealed the ocean away for billions of years. This offers unparalleled long-term stability, protecting any potential life within from surface radiation and dramatic temperature shifts. Furthermore, evidence strongly suggests Titan's ocean is in direct contact with a silicate rock core, a crucial prerequisite for the kind of hydrothermal vent chemistry we find so promising. Enceladus shares this rock-water contact, but its thinner shell and active venting could mean its ocean chemistry is more rapidly cycling and potentially less stable over geologic time. Europa's ocean is also thought to contact rock, but the constant, intense radiation from Jupiter bathes its surface, creating a hostile environment for any future surface missions and potentially affecting the upper layers of its ice. So, each ocean world presents a different strategy for habitability. Enceladus is the open book, readily sharing its secrets with anyone who flies by, but its ocean might be younger and its environment more dynamic. Europa is the vast, mysterious abyss, offering a huge volume of water with strong evidence for energy sources, but with a thinner shield against its radiant parent planet. Titan, however, is the deep, secluded vault. Its ocean is the most isolated, the most protected, and potentially the most stable over cosmic timescales. It represents the possibility of a biology that has been quietly evolving in utter isolation, completely independent of the Sun, for almost the entire history of the solar system. This comparison doesn't crown one world as more habitable than the others. Instead, it reveals a spectrum of possibilities. The outer solar system isn't just home to a few icy rocks. It contains a diverse collection of aquatic worlds, each following a different recipe for creating and maintaining a liquid ocean, and each offering a unique window into the potential for life beyond our Earth-centered imagination. This remarkable family of ocean worlds, all orbiting within the same planetary system, raises a profound and almost cinematic possibility. If life did indeed arise independently within the warm, dark ocean of Enceladus and is being constantly flung out into space through its powerful geysers, could some of those tiny microbial hitchhikers eventually find their way to Titan, seeding its isolated sea with life? This idea is a specific version of the theory known as panspermia, the concept that life can be distributed throughout the cosmos by traveling on asteroids, comets, or even dust grains. But within the tight-knit family of Saturn's moons, this isn't a far-flung interstellar journey. It's a local commute, and the mechanics of such a transfer are both fascinating and fraught with challenges. First, let's consider the journey itself. Enceladus, a small, vibrant moon, is continuously spraying a mist of water vapor and ice crystals from its south polar region. Embedded within this plume, scientists believe, could be microorganisms or at the very least complex organic molecules that represent the building blocks of life. These particles are ejected with enough force to escape Enceladus's weak gravity, but not enough to break free from Saturn's immense pull. So they don't shoot off into the void. Instead, they enter into orbit around Saturn, forming a tenuous, microscopic ring, a diffuse cloud of potential biological material. From this orbital perch, the particles are subject to the complex gravitational nudges of Saturn's other moons and the subtle but constant pressure of solar radiation. Over time, their orbits can evolve, drifting outward from Enceladus. The key question is whether any of these drifting particles could have an orbit that eventually intersects with Titan. The probabilities are low for any single particle, but we are talking about timescales of billions of years and an immense number of particles being ejected. Given enough time and enough material, the statistically improbable can become almost inevitable. It's a cosmic lottery with quadrillions of tickets being printed every year for eons on end. However, arriving at Titan is only half the battle. The would-be migrant then faces its greatest obstacle, Titan's incredibly thick atmosphere. Any particle entering this dense gaseous shroud would be subjected to intense heat from atmospheric friction. A large, sturdy chunk of ice might have its exterior vaporized but protect a pristine core inside, similar to how some meteorites survive their fall to Earth. But a fragile microbial spore encased in a tiny ice grain would be incredibly vulnerable. It would have to survive this fiery descent without being utterly sterilized by the heat. Once through the upper atmosphere, it would then parachute slowly down to the surface, landing not in the water ocean, but on the solid, icy crust, likely becoming embedded in the layers of tholin and organic gunk that cover the landscape. This is the second major hurdle. The life form, if it survived the journey, is now stranded on the wrong side of the kitchen door. It is sitting on the lid of the pot rather than in the soup. For it to reach the ocean, it would need a mechanism to get through Titan's monumental ice shell, which may be 60 miles thick. This is where Titan's own geology could potentially play the role of a delivery service. We discussed cryovolcanism earlier, where warm water ice wells up from below, but the process can also work in reverse through a mechanism called impact gardening or cryotonics. A large comet or asteroid impact on Titan's surface could, in theory, create deep fractures that temporarily connect the surface with the ocean below. Alternatively, shifting stresses in the ice shell could create conduits that allow surface meltwater to drain downward. If our hardy microbial traveler landed near one of these rare and temporary geological windows, it could be washed down into the depths. The chances are astronomically small, a series of lucky breaks stacked one upon the other, but in a universe that has had over 4 billion years to work with, we cannot completely rule out such a sequence of events. The result would be a form of directed panspermia, where life from one world is delivered to another within the same system, but this leads to a final, critical biological challenge. Even if a microbe from Enceladus could survive the vacuum of space, the radiation exposure, the fiery descent through Titan's atmosphere, and then be transported through the ice shell, it would then have to survive in Titan's ocean. The conditions there, the specific salinity, pH, pressure, and chemistry, might be completely different from its home environment. A microbe evolved for the specific hydrothermal vents of Enceladus could find Titan's ocean utterly inhospitable, a foreign sea where it cannot metabolize or replicate. In this scenario, the transfer would be a biological dead end. However, if the basic conditions are similar, both are saltwater oceans in contact with a rocky seabed and heated by hydrothermal activity, then the potential for success increases. The discovery that life on Earth can thrive in incredibly diverse environments, from subglacial lakes to boiling acid springs, suggests that life, once it gets a foothold, is remarkably tenacious. A microbe that made this incredible journey might not find a perfect home, but it might find a habitable one, and that could be enough to spark a whole new evolutionary tree on Titan, a branch of life with origins on another world. This possibility turns Saturn's system of moons from a collection of isolated islands into a potential archipelago, where life, if it exists, might not be confined to a single point of origin, but could be a shared phenomenon, a testament to the resilient and potentially contagious nature of biology itself. What Titan teaches us, then, is that our solar system is not the only possible model for a living world. For generations, our search for life beyond Earth has focused on a very specific and perhaps overly narrow category of planet, those orbiting within the so-called Goldilocks zone of their star. This is the orbital band where temperatures are just right for liquid water to exist on the surface, a zone that feels comfortably familiar because it's precisely where we find our own Earth. We have been scanning the atmospheres of distant exoplanets, looking for the telltale signs of water vapor, oxygen, and methane as potential biosignatures, all based on the assumption that life elsewhere will follow the same basic rules as life here. But Titan, a world so far from the Sun that water is frozen solid on its surface, shatters that assumption. It demonstrates that a sun-warmed surface is not a prerequisite for habitability. The energy for life can come from within, from the gravitational tug of a giant planet or the slow decay of radioactive elements in a rocky core. This single insight explodes the concept of the habitable zone, transforming it from a thin, delicate ring around a star into a vast, three-dimensional volume that encompasses the interiors of countless moons and planets, regardless of their distance from stellar warmth. This new perspective forces us to reconsider an entire class of previously overlooked worlds, both within our galaxy and beyond. Astronomers have already begun to identify exoplanets that defy our traditional categories. Some of the most common planets in the Milky Way are known as Hycean worlds, a term blending hydrogen and ocean. These are planets larger than Earth but smaller than Neptune, with thick, hydrogen-rich atmospheres enveloping global oceans of liquid water. While they might orbit closer to their stars than Titan does to the Sun, their surface conditions are likely shrouded in a perpetual, Titan-like haze, with high pressures and temperatures that could still support liquid water oceans beneath the clouds. Titan provides a crucial local model for understanding the complex organic chemistry that could be brewing in the atmospheres and on the surfaces of these distant Hycean worlds. If simple gases like methane and nitrogen can be transformed into the complex precursors of life in Titan's upper haze, then the same photochemical processes could be operating on a billion other worlds with similar atmospheric compositions, creating a cosmic drizzle of prebiotic material across the galaxy. But the implications reach even further to worlds that are truly Titan-like in their frigid isolation. Imagine a planet or moon unbound from any star, drifting alone in the cold darkness of interstellar space. For a world like Earth, this would be a death sentence, a rapid freeze into a permanent ice ball. But for a Titan analog, a rogue planet with a thick, insulating atmosphere and a heat-producing radioactive core, it could be a stable, long-term home. Its surface would be a frozen landscape of hydrocarbon ices, but deep beneath, a subsurface ocean could persist for billions of years, powered solely by internal heat. In the profound quiet between stars, cut off from all stellar energy, life could still flourish around hydrothermal vents on the ocean floor, its existence powered entirely by the planet's own inner warmth. The galaxy could be teeming with such nomad worlds, dark and silent from the outside but hiding vast, living oceans within. Titan shows us that these are not barren wastelands, they are potential arcs carrying the possibility of life through the emptiness of space. This radical expansion of habitable real estate has a direct and thrilling impact on the search for extraterrestrial intelligence. If life can emerge in the dark subsurface oceans of icy moons, then the most common form of life in the universe might not be surface-dwelling, technological civilizations like our own. It might be aquatic, living in perpetual darkness under miles of ice. Such life would likely never develop astronomy, as it would have no view of the stars. It might never invent radio technology, as its environment would be water-filled and opaque to our forms of communication. Their intelligence, if it evolved, would be utterly different, perhaps focused on sonar and chemical signals, their culture and science shaped by a world of pressure, currents, and geothermal energy. We might be surrounded by a galaxy filled with intelligent beings, but they are living in oceans beneath the ice, their presence completely hidden from our current methods of detection. This doesn't make them less intelligent, it simply makes them alien in a way we are only beginning to comprehend. Therefore, Titan's greatest lesson is one of profound cosmic humility and exhilarating possibility. It teaches us that life is not a fragile anomaly, a rare spark that requires the perfect, gentle conditions of an Earth-like world. Instead, it suggests that life is a tenacious and opportunistic process, capable of exploiting any available energy gradient, whether from a star or a planet's core, and of using whatever solvent is liquid, whether water or methane. The universe is not just full of potential Earths, it is filled with an unimaginable diversity of worlds, each with its own unique pathway to complexity. By understanding Titan, we are not just studying one strange moon in our backyard. We are calibrating our instruments and our imaginations for the thousands of exotic exoplanets we are discovering. We are learning to read a much broader set of biosignatures, to listen for a wider symphony of life. Titan stands as a testament to nature's boundless creativity, a working model that proves the ingredients for life are common, and the recipes are far more varied than we ever dreamed. Our solar system, with its hidden oceans and hydrocarbon seas, is likely not a singular wonder, but a standard template for a universe that is, in all probability, abundantly and wonderfully alive. This brings us to a profound responsibility, one that emerges the moment we shift from seeing Titan as a distant object of study to recognizing it as a potential abode for life. The very act of exploration, which seeks to answer whether we are alone, carries the risk of inadvertently providing the answer ourselves by contaminating a pristine world with our own microbial stowaways. This is the core dilemma of planetary protection, a field of ethics and protocol that treats space exploration not just as an engineering challenge, but as a form of interstellar environmentalism. The principles are straightforward but incredibly difficult to execute. We must prevent forward contamination, which is the transfer of viable Earth organisms to another celestial body, and backward contamination, which is the bringing of extraterrestrial material back to Earth. For a world like Titan, with its potentially habitable subsurface ocean, the protocols for forward contamination become paramount and incredibly strict. The concern isn't about a spaceship covered in obvious dirt. It's about the invisible, tenacious microbial life that clings to every surface we build. Certain extremophile bacteria, like Deinococcus radiodurans, are known for their incredible resilience, capable of surviving the vacuum of space, intense radiation, and extreme temperatures. These tiny hitchhikers could, in theory, endure the journey to Titan tucked away in a tiny crevice on a lander or rover. If that spacecraft were to touch down on the surface and then, either by design or accident, come into contact with the subsurface ocean, perhaps through a drill that penetrates the ice or by landing near a cryovolcanic fissure, these Earth microbes could be introduced into Titan's ocean. The consequences are unpredictable. They might simply die, unable to compete in an alien chemical environment. But there's a chance, however small, that they could find the conditions tolerable, thrive, and outcompete any nascent native life forms, effectively performing a microbial genocide before we even have a chance to discover them. We would have irrevocably altered or even erased the very biology we sought to find, turning a world of unique potential into just another place where Earth life exists. To prevent this, missions destined for sensitive locations like Titan undergo a rigorous sterilization process that is more akin to preparing a surgical instrument than building a spacecraft. Components are baked in specialized ovens at high temperatures for extended periods, assembled in ultra-clean rooms with stringent air filtration, and treated with chemical agents like hydrogen peroxide vapor. For a mission like Dragonfly, which is targeting the organic-rich surface but not designed to directly probe the ocean, the requirements are classified under a specific category that mandates a high level of cleanliness but not the absolute sterility required for a direct ocean access mission. The goal is to reduce the total microbial load to an acceptable level, a number calculated based on the probability of the spacecraft accidentally contacting a special region, a place where Earth life could potentially replicate. This involves meticulously cataloging every component, estimating its bioburden, and applying the appropriate decontamination steps. It's a painstaking and expensive process, but it is considered a non-negotiable cost of responsible exploration. However, the ethical considerations extend far beyond just technical cleanliness. They force us to ask a deeper philosophical question: what is our fundamental duty toward potential alien life, especially if it is still in its primordial, prebiotic stages? Do we have the right to interfere with its natural evolution, even with the noble goal of scientific discovery? Some ethicists argue for a principle of non-interference, suggesting that worlds with a high potential for indigenous life should be designated as wilderness preserves, off-limits to physical contact for the foreseeable future, studied only from orbit. They draw a parallel to the Antarctic Treaty, which designates the continent as a natural reserve devoted to peace and science, with strict rules to protect its unique environment. Under this view, Titan's subsurface ocean would be granted a kind of intrinsic value, a right to exist and evolve on its own terms, untouched by human influence. A counter-argument, and the one that currently drives exploration planning, is that our ethical duty is balanced by a fundamental need to know. The potential discovery of a second genesis of life would be one of the most significant events in human history, with profound implications for our understanding of biology, our place in the universe, and even philosophy and religion. To forever refrain from searching for it due to the risk of contamination could be seen as a failure of our curiosity and our intellectual destiny. The challenge, then, is not to avoid exploration altogether, but to conduct it with an unprecedented level of caution and foresight. This means designing future missions, particularly those intended to directly sample the ocean, as single-use probes that are sterilized to the highest possible standard, perhaps even constructed from materials that can be sterilized with radiation on the journey, and that are designed to remain sealed within the ocean after their work is done, becoming a permanent part of that environment rather than a continuing source of contamination. This leads to the most complex scenario of all. What if we discover life on Titan that is not just microbial but complex or even intelligent? While this remains highly speculative, the sheer scale and potential age of the subsurface ocean mean we cannot completely dismiss the possibility of macroscopic life forms. Our ethical framework would then need to undergo a radical shift, moving from planetary protection to something more akin to interstellar interspecies ethics. How would we communicate? What rights would such beings have? Would our presence, even as observers, constitute a harmful intrusion? These questions push the boundaries of our current ethical thinking, but they highlight the ultimate goal of planetary protection: to ensure that our first contact with alien life, if it ever happens, is an act of respectful discovery, not an accidental invasion. By grappling with these difficult questions now, as we plan our first tentative steps into Titan's mysterious depths, we are not just being cautious engineers, we are practicing a new form of cosmic citizenship, one that acknowledges our power to affect other worlds and accepts the profound responsibility that comes with it. Yet, with all these extraordinary possibilities for alien life, our imagination can't help but leap forward to a time when humanity itself might step onto those alien shores. The idea of colonizing Titan sounds like the pinnacle of science fiction, a dream for the far future. But when we move beyond the dream and into the realm of practical engineering, the challenges we face are as immense as the moon itself. The first and most obvious hurdle is the sheer, bone-chilling cold. With surface temperatures hovering around -290 degrees Fahrenheit, Titan is a world where exposed flesh would freeze instantly, and most earthly materials would become as brittle as glass. Our machinery, designed for terrestrial conditions, would seize up and shatter. Every single component of a habitat, from its structural beams to the hinges on its doors, would need to be specially engineered from alloys and composites that retain their flexibility and strength in a deep cryogenic environment. Simply keeping a human habitat warm would be a monumental energy challenge, a constant battle against a cold so profound it defies earthly comparison. Then there's the issue of resources, but in a strangely inverted way. Titan is often described as having abundant resources, but they are the wrong kind for human survival as we know it. The most glaring absence is liquid water. While a vast ocean of it lies beneath the ice, accessing it would require drilling through a shell potentially 60 miles thick, a feat of engineering far beyond our current capabilities. On the surface, the liquid is methane, which is useless for drinking or agriculture. The atmosphere, while thick, is almost entirely nitrogen with no free oxygen to breathe. So, a human colony would be utterly dependent on closed-loop life support systems, where every drop of water and every molecule of oxygen is meticulously recycled. A single system's failure would be catastrophic. This creates a colony that would feel less like a settlement and more like a spacecraft that has landed and never taken off. A fragile bubble of Earth-like conditions maintained at tremendous cost in the heart of an alien environment. Yet, for all these daunting obstacles, Titan does offer some surprising advantages that other worlds in our solar system lack. The most significant is its atmosphere. That thick, smoggy nitrogen shroud, which is a nuisance for astronomy, is a fantastic shield against cosmic and solar radiation. On the Moon or Mars, colonists would be exposed to dangerous levels of radiation, requiring them to live underground or in heavily shielded habitats. On Titan, the atmosphere provides a protective blanket equivalent to several feet of water, making the surface radiation environment relatively benign. This means colonists could potentially live on the surface, looking out at the landscape, rather than being confined to subterranean bunkers. Furthermore, the low gravity, about 1/7 of Earth's, would make construction easier and daily movement less strenuous, though it would come with the long-term health challenges of living in a low-G environment. The most frequently cited advantage is the abundance of hydrocarbons. The dunes are made of organic sand, the lakes are filled with liquid methane and ethane, and the atmosphere produces a constant rain of complex organic compounds. With the right technology, these could be processed into rocket fuel. In fact, Titan could become the solar system's ultimate gas station. A spacecraft could launch from Earth with minimal fuel, use Titan's resources to refuel for the return journey, or to journey further out into the solar system, dramatically reducing the cost and complexity of deep space exploration. The hydrocarbons could also be used as a feedstock for manufacturing plastics and other synthetic materials, potentially allowing a colony to become increasingly self-sufficient in producing tools and parts. So, what would a human outpost on Titan actually look like? Imagine clusters of massive geodesic domes, their shells made of multiple layers of incredibly strong, transparent material, designed to withstand the pressure differential and the extreme cold. Inside, the atmosphere would be a warm, breathable mix of oxygen and nitrogen. The domes would be lit by powerful, full-spectrum artificial lights to simulate a day-night cycle and to grow food in vast hydroponic farms. These farms would be essential as they would not only produce food but also contribute to oxygen production and water recycling. The landscape outside the dome would be surreal, a dim, orange-tinted twilight with a light, gentle rain of methane droplets sometimes pattering against the transparent roof. The ground would be a dark, sticky mixture of water ice and organic sludge. For power, the colony would almost certainly rely on compact nuclear fission reactors, as solar power is utterly futile so far from the sun. Life for the colonists would be a strange mix of the familiar and the profoundly alien. They might don heavily insulated suits not to protect against vacuum, but against the cold, perhaps with integrated heating systems powered by long-lasting batteries. A walk outside would feel more like a deep sea dive than a spacewalk, with the thick atmosphere slowing movement and creating a peculiar quietness where sounds are muffled and close. The social and psychological challenges would be immense. The crew would be isolated in the extreme, with communication delays to Earth of over an hour each way, making real-time conversation impossible. They would be a small community living under a golden haze, with the ringed globe of Saturn hanging motionless in the sky, a constant, breathtaking reminder of their incredible distance from home. Colonizing Titan wouldn't be about terraforming it into a new Earth. It would be about learning to live within it, to build a sustainable, permanent human presence in one of the most unforgiving, yet strangely alluring, environments our solar system has to offer. Yet for all the remarkable discoveries and compelling theories, Titan remains a world shrouded in profound mysteries, holding onto secrets that even our most sophisticated models cannot yet fully explain. These are not minor gaps in our knowledge, but fundamental puzzles that challenge our understanding of how this alien world operates. One of the most glaring enigmas revolves around the very gas that defines Titan's liquid cycle, methane. Sunlight, specifically ultraviolet radiation, is exceptionally efficient at breaking apart methane molecules in the upper atmosphere. The calculations are clear. Based on the rate of this destruction, the methane we see in Titan's atmosphere and seas should have been completely depleted by solar photochemistry in a relatively short period, astronomically speaking, perhaps just a few tens of millions of years. Yet Titan is ancient, over 4 billion years old, so a glaring question remains: what is constantly replenishing the methane? Where is the faucet that keeps it flowing? Scientists are actively investigating several potential sources for this mysterious methane resupply. One leading hypothesis points back to the interior, suggesting that cryovolcanic activity could be periodically releasing methane stored in the moon's interior or produced by geothermal reactions deep within the rocky core. This would act as a slow, geological methane tap, releasing fresh supplies to offset the losses in the atmosphere. Another possibility involves a massive reservoir of methane clathrate, a type of ice that traps methane molecules within its crystal structure existing somewhere beneath the surface, perhaps at the boundary between the ocean and the icy shell. Changes in temperature or pressure could cause this clathrate reservoir to slowly destabilize, seeping methane upward over geologic time. A third, more speculative idea is that a form of methanogenic life could be producing it, similar to certain microbes on Earth, but this is considered a last resort explanation, as non-biological sources must be ruled out first. The true answer likely involves a combination of these processes, but pinpointing the dominant mechanism is crucial, as it would reveal whether Titan's active surface is a temporary phenomenon or a stable feature that has persisted for most of the Moon's history. Switching our gaze from the sky to the hidden depths, another major puzzle concerns the very structure of the global subsurface ocean. Is it a single, well-mixed body of water, or is it stratified into distinct layers like a cosmic cocktail? The distinction is critical for habitability. A well-mixed ocean would efficiently circulate nutrients and energy, potentially creating a more uniformly habitable environment. However, data from Cassini suggests another possibility. that Titan's ocean may be what scientists call a non-convecting or stratified ocean. In this model, the upper layer of the ocean could be incredibly dense and salty, perhaps even supersaturated with salts like sodium sulfate or sulfur compounds. This heavy, briny layer would act as a lid, preventing the vertical mixing of water. Beneath it, a deeper layer might be less salty and in contact with the rocky seafloor. This stratification would have profound consequences. It would effectively create two separate aquatic environments. The deep layer, in contact with the hydrothermal vents on the core, could be rich in chemical energy and potential building blocks for life. But if a dense, stagnant layer of brine sits above it, it could trap that life-sustaining chemistry in the depths, preventing it from rising to enrich the upper ocean and the base of the ice shell. Any life that originated near the vents might be forever confined to the abyssal plains, unable to spread upwards. Furthermore, the interface between the different layers could host unique and complex chemistry of its own, as different solutions slowly diffuse into one another. Determining the true structure of Titan's ocean is a top priority, as it will tell us whether we are looking at a world with a single, connected biosphere or one where life, if it exists, is trapped in isolated pockets. Perhaps the most visually captivating and bizarre mysteries are the so-called magic islands. During its mission, the Cassini radar imaged the same areas of Titan's large seas, like Ligeia Mare, multiple times. In several instances, bright, island-like features appeared in one observation only to vanish completely by the next flyby days or weeks later. These weren't permanent landmasses, they were transient phenomena, earning their enchanting nickname. What could possibly be causing patches of the sea surface to become radar bright, meaning they reflect the radar signal back strongly and then disappear? Several intriguing explanations are on the table. The most plausible theories involve processes that create bubbles or floating solids on a temporary basis. One idea is that these features could be vast fields of nitrogen bubbles. As the seas warm slightly during Titan's long seasons, dissolved nitrogen gas could fizz out of solution, much like carbon dioxide bubbling out of a soda. A massive release of these bubbles would create a frothy, choppy patch on the sea surface that would scatter radar waves effectively, making it appear as a bright island. When the bubbling stops, the patch would calm down and vanish from radar view. Another possibility is that they are floating solids, perhaps large slabs of porous hydrocarbon ice that form on the surface and then sink, or organic solids that clump together, float for a time, and then become waterlogged and sink. Some scientists have even suggested they could be waves, not small ripples, but large swells driven by winds, though Titan's seas are typically exceptionally calm. The true nature of the magic islands remains one of Titan's most delightful puzzles, a reminder that even with a spacecraft in orbit, this world can still perform tricks that leave us wondering, challenging our assumptions and inviting us to look closer. So, after this grand tour of methane seas and hidden oceans, what are we to make of this enigmatic world? Titan is far more than just another moon. It stands as a profound second chapter in the story of our solar system. We have for so long viewed Earth as the solitary experiment in planetary biology, a unique and perhaps fragile occurrence. But Titan presents us with an entirely separate laboratory, one that has been running its own chemical reactions for billions of years, independent of our own. It demonstrates that the processes that lead to complexity, the cycles of evaporation and rainfall, the erosion of landscapes, and the synthesis of complex organic molecules are not exclusive to our planet. They are universal physical principles that can operate with whatever ingredients are at hand, even in the bitter cold of the outer solar system. This forces a fundamental shift in our perspective. Our search for life has been constrained by a kind of planetary chauvinism, a bias toward worlds that look and feel like our own. We have instinctively searched for liquid water on sun-warmed surfaces, for oxygen-rich atmospheres, for conditions that mirror those of our own cradle. Titan shatters that narrow framework. It boldly suggests that the recipe for life might not be a single, rigid formula, but a versatile set of principles that can be adapted to a stunning variety of environments. The essential ingredients may not be water and sunlight, but rather a liquid solvent, a source of energy, and a continuity of complex chemistry over time. By proving that these conditions can be met in a place so utterly alien to us, Titan massively expands the real estate of the cosmos that we must consider potentially habitable. The implications of this are staggering for our place in the universe. If a single solar system like our own can host two worlds with such powerful, albeit different, potentials for life, then the probability of life being a common phenomenon throughout the galaxy skyrockets. We are no longer looking for a needle in a haystack. We are realizing that the haystack itself might be made of needles. The galaxy could be filled with Titan-like moons orbiting gas giants, with icy worlds drifting between stars, each holding the possibility of a hidden biosphere thriving in absolute darkness. This doesn't just increase the likelihood of finding simple microbes. It suggests that the universe might be teeming with a diversity of life forms so vast and strange that our current imagination cannot yet encompass them. We may be on the verge of discovering that life is not a rare and precious miracle, but an almost inevitable outcome of cosmic evolution. Therefore, Titan's greatest gift to us is not a specific discovery, but a new framework for humility and wonder. It teaches us that our own evolutionary path, while precious to us, is just one possible trajectory among many. The life we know, based on DNA and water, could be merely one branch on a vast and sprawling tree of biology. There could be entire kingdoms of existence built on different genetic molecules, metabolizing different energy sources, and perceiving time and reality in ways we cannot fathom. By studying Titan, we are learning to read a much broader language of life. We are calibrating our instruments and our minds to recognize biosignatures that have nothing to do with our own. This world, hanging in the golden haze around Saturn, is our local tutor, preparing us for the day when we point our telescopes at distant exoplanets and know what other, more fantastic signs of life to look for. It is a constant reminder that the universe is far more creative, more generous, and more mysterious than we have ever dared to believe. The story of Titan is far more than a tale of a distant moon. It is a fundamental challenge to our cosmic self-image. For generations, we have gazed at the stars from our warm, water-rich world, assuming that the conditions for life were a rare and delicate recipe, one that required the gentle light of a sun. We confined our search for neighbors to a thin, hopeful band around other stars, the so-called Goldilocks zone. But Titan, shrouded in golden haze and bathed in a cold deeper than any earthly winter, forces a radical reconsideration. It demonstrates that the essential ingredients for life are not sunshine and surface oceans, but something far more universal. A liquid medium, a source of energy, and the relentless, patient work of chemistry over deep time. This realization doesn't just add one more candidate to our list of potentially habitable worlds. It explodes the list altogether, transforming the icy moons of the outer solar system from frozen curiosities into the most promising real estate for biology in our cosmic neighborhood. As we prepare to send Dragonfly on its journey to this enigmatic world, we are not merely launching another robot. We are sending a detective to the scene of a potential crime of creation, tasked with looking for clues that a second genesis of life may have occurred. The implications of what it might find stretch far beyond the realm of astronomy. If Dragonfly's instruments were to detect the chemical signatures of a metabolism, the unexplained depletion of hydrogen, the subtle preference for one-handed molecules, it would do more than confirm life on Titan. It would provide the first concrete evidence that the emergence of life is not a singular, miraculous fluke that happened only once on our planet. It would powerfully suggest that biology is a natural, almost inevitable outcome of cosmic evolution, a process that unfolds wherever the conditions are even remotely suitable. This would fundamentally alter our understanding of our own place in the universe, transitioning us from a species wondering if we are alone to one that knows with certainty that we are part of a vast living cosmos. This new perspective forces us to look back at our own planet with fresh eyes. The discovery of a truly alien biosphere built on a chemistry independent of our own would revolutionize the field of biology itself. By studying a life form that does not share a common ancestor with anything on Earth, a second genesis, we would finally have a comparative sample. We could ask profound questions that are currently unanswerable. Are the molecules of inheritance always long chains? Is the cellular structure the only way to create order? Are there universal laws of biology just as there are laws of physics? The answers would provide a deeper context for life on Earth, helping us understand which aspects of our biology are essential and which are merely accidental details of our specific evolutionary path. Titan offers the potential for a grand cosmic experiment, one that could unlock the fundamental rules of living systems. The journey to Titan, therefore, is a journey into our own future. It is a test of our maturity as a species, challenging us to explore with both boldness and profound responsibility. The strict protocols of planetary protection, the careful sterilization of spacecraft, are not just bureaucratic hurdles, they are an expression of a new ethical stance toward the universe. They acknowledge that we have the power to affect other worlds and accept the duty to preserve their natural states for study. As we stand on the brink of these discoveries, we are practicing a form of cosmic citizenship, learning to interact with potential alien life not as conquerors but as respectful guests. The success of this endeavor will be measured not just by the data we bring back, but by the wisdom we demonstrate in obtaining it. Ultimately, the hidden oceans and alien chemistry of Titan gift us with something priceless, a broader imagination. They teach us that the universe's creativity vastly exceeds our own. Life, in its boundless ingenuity, may exist in forms we have not yet dared to dream. Slow, patient beings in dark oceans or fragile chemistries unfolding in hydrocarbon seas. As Dragonfly takes flight in the thick air of that distant moon, it carries with it our collective curiosity and hope. It flies toward answers that could redefine life itself, reminding us that the greatest discoveries often lie not in finding reflections of our own world, but in encountering the truly magnificently